Good morning, students. Today we are going to see the chapter number 1, Introduction to MEMS. Myself, Madhuri Mulik, working as an assistant professor in Department of Electronics and Telecommunication, Sharad Institute of Technology, College of Engineering. So, in a previous lectures, we have seen the chapter number 1, that is Introduction to MEMS. So, in that we have covered the all remaining parts of history, scaling property, then fabrication process, then the methods of the fabrication. Then in this session we are going to see the future of MEMS. So there are lots of challenges in industry. So let us see the industry challenges. So some of the major challenges facing the MEMS industry include, that is, access to foundries. So in this challenge, MEMS companies today have very limited access to MEMS fabrication facilities. So due to that, foundries for prototype and device manufacture facing the problem where the limited access for the MEMS compounds. So in addition, the majority of the organizations expected to benefit from this technology currently do not have the required capabilities and competencies to support MEMS fabrication, because MEMS fabrications are working on that the micro scales. So due to that, whatever the manufacturing devices or protocols required, that have to be designed well, and then and only then the fabrication process is easy. Means, for example, telecommunication companies do not currently maintain micro machining facilities. So for the fabrication of optical switches, so affordable and receptive access to MEMS fabrication facilities is crucial for the commercialization of MEMS. So, in history and as well as in introduction of this chapter, we have seen that the MEMS is nothing but the micro electro mechanical system. So, whenever we are going to design any micro system, so we have to take into the consideration of that the scaling laws which is required for the MEMS devices or system. So, at that time, we have seen that very uh, micro components we have to design, and over that we have to means using that the bulk micro machining or surface micro machining, we have to fabricate that devices. So these methods also, if you have seen, then they have to be carried out very carefully, as well as that the dimensioning they have to prove that it is nothing but the micro devices. So the affordable and receptive access to the MEMS fabrication facilities is crucial. So due to that, for the commercialization of the MEMS, they are getting the difficulties. Next, design, simulation and modeling. So, due to the highly integrated and interdisciplinary nature of MEMS, it is difficult to separate device design from the complexities of fabrication. So, consequently, a high level of manufacturing and fabrication knowledge is necessary to design a MEMS device. Furthermore, considerable time and expense is spent during this development and subsequent protocol stage. So, in order to increase innovation and creativity and reduce unnecessary time to market costs, An interface should be created to separate design and fabrication. So three main important parts why we are fabricating the MEMS device, that is design, after that simulation, and then actual modeling. So the MEMS devices are highly integrated and interdisciplinary in nature. How it is interdisciplinary in nature? Because the MEMS devices we can use in a biomedical applications, as well as in engineering, as well as in a communication, as well as that the day-to-day life home appliances application. So it is, and that the design is on the micro scale level. So it is highly integrated as well as the interdisciplinary nature. So the task to design that highly integrated and interdisciplinary, it is difficult to separate device design from the complexity of the fabrication. So high level of manufacturing and fabrication knowledge is essential to design the MEMS devices. So after that, if you considering the time and expense during that the development and subsequent protocol stage, so in order to increase innovation and creative and the reduce unnecessary time to market costs, so an interface should be created to separate the design and fabrications. So, as successful device development also necessitates modeling and simulation. So, it is important that MEMS designers have access to adequate analytical tools. So, currently, MEMS devices use folder design tools and are fabricated on a trial and error basis. So therefore, more powerful and advanced simulation and modeling tools are necessary for accurate prediction of MEMS device behaviors. So there must be a research and development while we are modeling and simulate that whatever the designer designs. So that design must be follow the analytical tool, and in a traditional methods for that the design tools and fabrications are used, which are the trial and error basis. So that's why there is a need of the powerful and advanced simulation as well as in a modeling tools. The next thing is packaging and testing. So the packaging and testing of devices is probably the greatest challenge facing the MEMS industry. So as previously described, MEMS packaging presents unique problems compared to the traditional IC packaging in that MEMS package. So typically must provide protection from an operating environment as well as enable access to it. So currently there is no generic MEMS packaging solution, with each device requiring a specialized format. So consequently, packaging is the most expensive fabrication step and often makes up 90% or more than that of the final cost of the MEMS device. So why the packaging and testing is important? Because every that the module or that the device in electronics is first upon tested and then packaging. Packaging of that device is important because all of the electronics devices are nothing but sensitive to the temperature or as well as the surrounding environment. Okay, because they are nothing but the semiconductor material is used inside to fabricate any type of that the device. So in MEMS also most important material is nothing but the silicon substrate. So that's why there is a again we have to think related to that the behavior of that the material. So we have to protect from that the outer environment, but in a fabrication process also itself we have to maintain that environmental to device enable to access all that things. So whenever the final product is uh, done, at that time we have to place the well package for that device. If that package is not well, then it get interacted to the outer environment and it will not going to uh, act according to our prediction. So that's why the packaging and testing is very important while we are fabricating the MEMS. Then next is the standardization. So due to the relatively low number of commercial MEMS devices and the pace at which the current technology is developing, standardization has been very difficult, because every that thing whatever we have designed and developed, that must be standardized by using some of the reference things. But in a MEMS there is a low number of commercial devices, so that's why there is a piece at which the current technology is developing in. So how to standardize that, that is difficult one. So to date, high quality control and basic forms of standardization are generally only found at multi-million dollar or in a billion dollar investment facilities. So however, in 2000, progress in industry communication and knowledge sharing was made through the formation of MEMS trade organization. So there is a must be, we have to adopt some standardization where we can compare our product with that, and we are make again that the benchmark for that the standardization of that device. Then in again standardization based in Pittsburgh, USA, the MEMS industry group, that is MEMS IG, with founding members including X-Ray, Corning, Honeywell, Intel, and JDS, Uniphase, grew out of study teams sponsored by DRPA that identified a need for technology road mapping and a source for objective statistics about the MEMS industry. So in addition, a MEMS industry roadmap sponsored by the Semiconductor Equipment and Materials. So international organization, so that is SEMI, that is Semiconductor Equipment and Material International Organization, has also been identified to share pre-competitive information on the processes. So the technology application and the markets for MEMS. So this web-based organization can be found out by using the following that the link. So that is http www.roadmap.nl. So these are the some organizations which develop the standardization related to that the MEMS market. Then several other European initiatives supported by government and the European Commission have been coordinated. So Euro practice, that is Microsystem Service for Europe Nexus, that is Network of Excellence in Multifunction Microsystem. So that aimed at enhancing European industry competitiveness in the global marketplace, and NetPack, whose role is to drive the development and use of advanced packaging and integration technologies. So the networking of these smaller companies and organizations on both a European and a global scale is extremely important and necessary to lay the foundation for a formal standardization system. So there is again that the network of excellence in multifunction microsystem is used to enhance the competitiveness as well as that the global marketing for that the MEMS devices. Then next feature of MEMS is education and training. So the complexity and interdisciplinary nature of MEMS require educated and well-trained scientists and engineers. So from a diversity of fields and backgrounds, because MEMS is related to the micro scaling, so it have to he or she have to the knowledge of that the micro scales. Then it is interdisciplinary, so that scientist or that engineer must have the knowledge from the every area. Maybe it is medical, maybe it is at the communication as well as in any other marketing. So all type of the knowledge that scientists must have. So that's why it is interdisciplinary. Then diversity of field and that the backgrounds related to that the knowledge. So the current numbers of qualified MEMS specific personnel is relatively small and certainly lower than present industry demand. So less number of the qualified MEMS specific personnel as compared to the present industrial demand. So education at graduate level is usually necessary, and although the number of universities offering MEMS based degree is increasing. So gaining knowledge is an expensive and time consuming process. So there must be who is that the scientist which going to design the MEMS must be well educated as well as the well trained in all in order to handle complexity and interdisciplinary nature of that the MEMS. So that's why there are MEMS based degree is increasing, but gaining knowledge is an expensive and time consuming process. Then, therefore, in order to match the projected need for these MEMS scientists and engineers, an efficient and lower cost education methodology is necessary. So one approach, for example, in industry-led or driven academic research centers offering technology-specific programs with commercial integration, training, and technology transfer. So there are lots of main scientists are gathered and they are driving an academic research center which will provide technology specific programs with the commercial integration, as well as they are providing training and technology transfer so related to the MEMS. So anyone can get easily interact with that the MEMS design process. So in this session, we have seen the industry challenges, that is access to foundry, design, simulation and modeling, then packaging and testing, then standardization, then education and training. So this is nothing but the last point from our first chapter. So let us take the one overview which points we have discussed in the chapter number 1, because in previous for this chapter 1 sessions we have seen the first chapter, that is introduction to MEMS. So in that we have seen what is meant by MEMS, then history for the MEMS, then concepts of the MEMS, so principle of that working, applications and design, as well as we have seen the scaling properties issues for that the MEMS. Then micro machining process we have seen, in that bulk micro machining and surface micro machining. So in that substrate, lithography, wet, dry etching processes, as well as deposition process we have discussed. Then film stress, exhaustive process, as well as after that we have seen the mechanical transducers. So In that mechanical transducers, transduction methods, then accelerometers, gyroscope, pressure sensors, MEMS microphones, mechanical structures and actuators we have seen in that. So here our first chapter is finished up. So any doubts you can ask me. Thank you.